Okay, so this is the last video for this topic, system of particles and rotational motion. And after that, we will try to solve few questions from your previous NEET exams. So let's continue here. So angular momentum, we have discussed already about it. So little bit more we are going to discuss in this video. So in this video, we are going to discuss in a detail. So let's say we have an extended body here. This is extended body, and this is made up of n number of particles. And if this body is rotating about this axis, let's say this is z axis, and we will choose a standard unit vectors along these axes. So let's say this is y axis and this is x axis. So for n number of particles, let us consider one random particle. Let's say this is ith particle. So position will be ri with respect to this axis, and if this body rotates about this z axis, the angular momentum will be omega, and this omega we can write, if its magnitude is omega, we can write omega k cap, because this is along z axis if this body is rotating. Now this particle will follow a circular path which is in xy plane. Here this is x axis. So this particle, let's say, have mass m, and its velocity is, let's say, this is vi. And now let me write all these things here. So its position is ri, and we can write it ri, and along positive y, so we can write it ri j cap. And what about velocity? So velocity, these two things are in xy plane. This is along negative x axis, so we can write its magnitude times unit vector here, minus I cap. Now, what about angular momentum of this body here? Let's say this is Ci, center of this circle, which is lying on this axis of rotation. So let's say we are trying to get what is Li here. It will be Ri cross Pi, and then it will be Ri cross P, can be written as Mi Vi. So we can write it further. Mi is a scalar quantity, we can take it out, and then we will have Ri cross, and Vi can be written as, look, Vi can be written as omega I cross Ri. And if we try to know what is its direction, so we can take it omega I, and let's say, look, each and every particle has same omega here, so no need to write specifically I here. So it will be omega only, because if it is rigid body, each and every particle will complete one revolution about this axis in the same time. So angular velocity will be the same in magnitude, and if its rotation is only along this direction, its direction will be also the same. So let me write omega only here, and this omega is along k cap, and cross ri can be written as ri, and where it is, this is ri, so this will be j cap. So we can write here mi we have taken out, so vi can be written as here omega times ri, and k cross j will be minus I cap. So we can write it omega ri and minus I cap here. So this is what we have now. Now we can further proceed here, and then we will have mi. Ri can be written as, once again, look, this is a scalar quantity, so we can take it out, omega times ri. Then we will have ri cross minus I cap, and again we can write mi omega ri. Ri can be written as magnitude ri, and then its direction, which is j cap cross minus I cap, and ultimately it will be mi omega ri square, and this j cross I will be k cap. So Li can be written as this. Now, if we want to know what is the total angular momentum, this, so we have to sum this Li for n number of particles. So we can write it summation m I, sorry, I equals to 1 to n, 1 to n, and then we will have m I r I square omega and k cap. Okay. Now we will have here, look, this part is nothing but moment of inertia for this rigid body. So this is what we have as angular momentum of this body, this rigid body. Okay. And this angular momentum is along the positive z direction. But here we have a problem. And the problem is, look, if we are taking n number of such particles, then we will have Ci equals to C1 from C1 to Cn, means n number of centers will be there for each and every circle here. Okay, this is one thing. Or if you are trying to choose that, no, I am not going to choose each and every points here, means centers of these circles. I am not going to choose them as a reference for position Ri, and rather I am choosing this origin to be a common reference point for all these particles, then we will lose what means we are losing actually one information, one piece of information here. And what is that? We are considering only, let's say this is Ri with respect to O. So this is position vector with respect to this origin for this particle. So here we are losing one thing. We are considering only this component which is perpendicular to this z axis, and we are losing this component of position vector in our discussion. So let us try to bring this thing also into the picture, and then let's see what is happening. So here we have a rigid body, and here we have a rigid body, and this body is rotating about this axis, z axis. This is y axis and this is x-axis. Now, if we are choosing a random ith particle here, let's say this is first particle here. So if we are choosing first particle here, its position vector will be R1. Okay. And let's say its mass is M1. And its velocity, let's say this is rotating about this axis. So it will follow a circular path here. And this is the center. So its velocity, let's say it is in xy plane. So let's say it is along minus of this means minus I, that is opposite of this positive x. So we can write it has velocity something v1. Okay. And now we can write it has some momentum. So let me write it a little bit more elaborative way. So R1 can be written as, look, it has one component, R1 has one component which is perpendicular to this z axis, and another component which is along this z axis. So let's say this is R parallel for this R1, and this is its perpendicular component. We are taking this z axis to be reference for this perpendicular or parallel. So we can write this R1 has two components. One is R1 parallel, and this is along k cap, and another is R1 perpendicular, and this is R1 perpendicular, and this is along j cap. So here we are taking unit vector along y axis j cap, here along this k cap, and along x I cap. Okay, so we have position vector. What about velocity? So velocity vector, let's say this is along minus, at this point it is along minus I cap. So we can write v1 minus I cap. Okay, now we can write what is angular momentum for this particle L1. So this angular momentum can be R1 cross P1, and then we can write R1 is into its component form R1 parallel k cap plus R1 perpendicular j cap and cross. P1. P1 is m1 times v1, and v1 is along minus I cap. So we can write v1 minus I cap. So this is what we have. And if we try to solve it, so let me write it P1 only here instead of m1 v1. Let me write it P1 only. So P1 minus I cap, because the direction of velocity will be along the same as the direction of momentum, because this is mass times velocity now. So we know that momentum, linear momentum is mass times velocity. So the direction thing is decided from velocity. So we can write here R1 parallel times P1, and this will be K cross minus I. So it will be along minus J cap. Okay, because K cross I is going to be J cap. Next, R1, this one done. R1 perpendicular. So R1 perpendicular, and then P1, and then this is J cross I, minus I actually. So it will be along K cap. Now you can see here this angular momentum, if we are choosing this origin as a reference and taking position vector with respect to this. So this angular momentum of the first particle is, now it has two different components. One is L1 y, which is perpendicular component, means perpendicular to the z axis or axis of rotation. So here it is along negative y direction, and another is L1 z, and it is along positive z direction. So we can see here that angular momentum is now not only along the positive z direction, rather it is a sum of two different vectors here. So we can say angular momentum, or let me write it in notation only, this L1 is not in the same direction as omega is. Means angular velocity and angular momentum here are not along the same direction as it happens in case of linear momentum, because linear momentum and linear velocity, these two things are along the same direction, but this is not the case for angular momentum and angular velocity. So here we have a point to be noted. Now if we are taking one more particle, let's say here a second particle here at this point, just we can say just a type of mirror thing here, means symmetric about this z axis or axis of rotation. So it will have a velocity along positive x direction. In that case, here v1 will be, means let's say this is another particle, let's say this is second particle. So for this particle, velocity will be along positive I cap. This will be along positive x direction. And then when you go for r cross p, instead of here, look, this is k cross minus I. It was minus j cap, but k cross I will be, look, if you are putting here v1 instead of, let's say, v2 I cap, and then you are going to do it r cross p. In the second case, you will get this component equal in magnitude. This will be, let's say, this length is also equal to this length, means the radius is equal for the same circle. So this r1 p1 will be same in magnitude for r2 p2 here, but this j cap will be appearing here instead of minus j cap. So in such case, if you are adding these two angular momenta, L1 plus L2, you will get this angular momentum cancelling out each other. So the net will be only along z cap. The net will be only along angular momentum towards positive z direction or along k cap. So this is what is happening in case of a body which is a system which is symmetric about the axis of rotation. So we have a second point here which is to be noted. So in case the rigid body is symmetric about the axis of rotation, it will have only z component as its angular momentum, and the perpendicular components will be cancelling out each other. So, but we are talking about here in general case. So, in general, the body may not be symmetric. This may be asymmetric about z-axis. So, in that case, asymmetric, we will have two components here for this. In this case, we can do one thing, we can add all these things to get total angular momentum in case of asymmetric. And here symmetry will be decided based on this axis of rotation. So the body which we are considering should be symmetric about this axis. So if it is not, then we will have this expression L equals to, this is I equals to 1 to n if there are n number of particles. So this will be I equals to 1 to n, and then we will have one component which will be parallel to the axis of rotation, or let's say it is along k cap or maybe minus k cap based on the direction of rotation, means clockwise or anti-clockwise. Here if it is clockwise rotation, it will be minus k cap, and another, in this case we have anti-clockwise rotation of this rigid body viewing from the top. So its angular momentum along k cap. So that's why I'm writing here k cap only. It may be minus k cap if the body rotates in the opposite manner. So, and there will be a perpendicular component which will be along j cap or minus j cap based on the net angular momentum after adding all these components for each and every particle in revolution. So we will have these two things in case of angular momentum. And that's why I'm saying this angular momentum is not completely along this z-axis, but the angular velocity is along the z-axis. So I have already mentioned this point here, which should be taken, that angular momentum along z-axis may be in the symmetric case only, but this is also happening if the body is asymmetric. The angular momentum may not be along the angular velocity. Now we have a last topic here to discuss. Already we have discussed about that topic, but let me summarize here. This is conservation of angular momentum. Okay, so if there is no net external torque, this is no net external torque, that is 0, then dl by dt is 0, or you can say L is constant, and we know we can write L equals to I times omega, which will be constant. Okay, so I'm giving you a real life example for this. You might have seen such experiments that a person is sitting on a revolving table. Let's say this is revolving table which can revolve about this axis, or maybe its top can rotate about this axis, and a person is sitting or standing on this table, let's say, and he is holding two masses here, let's say two equal masses here, a kind of dumbbell thing, let's say. It may be any mass. Okay, so if someone pushes this revolving table and brings it into rotation, so this will start rotating, and then after once it has been set to rotate, no one is interfering here its motion, so there is no net torque in this case. And what you have observed, if you have seen such experiment, if this person brings these two masses near to the axis of rotation, that is passing through his body or her body, so if he is bringing these two masses near to this axis of rotation, he starts rotating faster, that is angular velocity increases. Why it happens? Because if there is no net torque, this I omega should be constant. And if you are bringing these masses closer to the axis, so you are reducing the position and hence you are reducing m into r, hence you are reducing m into r square, and hence you are reducing I. And then if you are reducing I and I times omega is constant, this should increase. And this you might have observed. And once again, if you put it back to original position, the omega or angular velocity will again decrease back to the original. Okay, this is all for this video. So thank you.